So in the last class, we were talking about the distributed consensus in the permissioned blockchain model. So the one which is used is your Paxos. So the Paxos Basics, we have seen in the previous lecture that the Paxos is based on your state machine replication. So in the state machine replication, so that state machine replication is associated with every user in the network, so that that act as your smart contract in that. So the proposers and the acceptors, they maintain the state of the running approach. So as we saw that in Paxos, there are three types of nodes. One is your acceptor, and the another one is the proposer, acceptors, proposers, and third one is the learners. Right? So these acceptors and proposers plays a major role, and the learners will, the this type of nodes are all that covers proposers as well as your acceptors when everyone agree to a particular consensus. So in this Paxos, the proposers and acceptors, they use a variable called the proposer ID, where the P is an epoch number that gives what is the new proposal, whether it is a new proposal or the old proposal, that maintains the status of this. And second one is the Paxos, the run aim at reaching a single consensus. Every user in the network, they comes to a single agreement. So that is like your smart contract in Bitcoin. So once they reach to a single consensus, then the Paxos cannot, the progress to another consensus that, they have committed to that, and they will try to execute that one successfully in a non-deterministic manner. So to reach the multiple consensus in this Paxos, one need to run the Paxos in rounds for multiple Paxos. So how that will be, we'll try to check it out in today's lecture. One is, as we said, there are the proposers and the acceptors will be there. So proposers will propose any, wants to propose any choice or any value. That means you don't want to go to the dinner or want to go to movie or whatever is there that become the value here. So then the proposer sends a proposer ID of that propose to the majority of the acceptors in the network, or maybe all of the acceptors in the network. So then try to wait for their response for that particular proposer. So that is, prepared the ID with the ID number, like the 100, the value, and the value, maybe it says that let's go to dinner. The value of this says that let's go to dinner, suppose. So then that proposer, received, when it is broadcasted, that will be received by every user in the network, every acceptor in the network. So then the acceptor will decide based on this prepared ID. This ID must be a unique across the proposers. It should not be same proposer of any others. Okay, so that will reduce the duplication in the network. So it must be unique across the proposer for this prepare ID message. Then every user in the network or proposer, they simply use the hash function which we discussed in the permissionless blockchain. So that hash function use the timestamp that gives whether it is a new one or the older one, along with the proposer ID, to generate a new proposer. So upon receiving this proposer, the prepare one, this of this proposer, every node will accept, and based on that proposer's uniqueness, they will try to decide did I promise to ignore the request with this IDP or not? They will check, every acceptor will check that whether they have committed to that proposer value or not. If committed, then if already committed, then this proposer message will be ignored. If not committed, then we'll promise to they ignore any request that is lower than this. Any previous requests are there, they will be ignored, and gives the reply to the proposer with the promise of that ID, that or commitment to that ID, that yeah, I will be in for that particular let's go to in dinner value. Okay, so that response we call the prepare ID and promise ID is used in Paxos. Right? So when the from these acceptors, suppose acceptor 1, 2, and 3, when the majority of acceptors given the response that we'll go with that particular value, based on that they will reach to, if the majority of acceptors promises with the same ID that can pass through the protocol, so the acceptor agrees and agrees on the state that we'll go with this promise, the prepare that the value which is proposed by the proposer. So then they reach to the protocol, the consensus protocol algorithm. So for that, the proposer gets the majority of promises, messages for the specific IDP, that is 100 in this case, and that sends the accept request IDP and the value to all the majority of the acceptors, that okay, let's my proposer is accepted by everyone, so let's go to dinner. So that information will be given, that it picks any value of its choice by the proposer, that okay, let's go for the dinner. So that the response will be given by your proposer to all the acceptors. So upon receiving this value by these acceptors, the IDP value and your the value that is go for the dinner. So then the acceptors will again recheck on their commitment, that did I promise to ignore the request with this IP ID or not. If yes, then they will ignore. If no, then reply with the accept ID and value, that also send it to all the learners. So everyone agreed, so that will send it to all the participants in the network, so they will become the learners. All are become the learners. Yeah.
Is the state of being a learner just once a decision has been made? That's what we classify every node?
Yeah, that is right. Yeah. So then once everyone agreed to go for the dinner, then all the nodes in the network, they become the learners. So that is first proposer, second the acceptors, and third the proposer and acceptor become the learners. So everyone accepts and go for the dinner. So this is the basic algorithm of your Paxos, that if the majority of acceptors accept the proposer and the value, then they reach to the consensus. Every agreement is done. So consensus is reached on that value, not on the IDP. Consensus reached on the value that is go for dinner. Right? So after that, they try to execute the proposer or the learner. Everyone become the learner in this case. Learner gets accept this message. Every node will get accept this message with the IDP and the value go for the dinner. If the proposer or learner gets majority of accept for this specific ID, then they know that the consensus is reached for that value, not on the IDP proposed one. So then during that, this happens with the single proposer in Paxos, but there is a possibility of your multi-proposers also in that group, in that network. So the first proposer, the ID, the value is accepted by every acceptor, and later second proposer is proposed with the new proposal, that the prepare ID with the 50, and that will be broadcasted in the network. Okay, so then the acceptors will receive this message or this proposer from this proposer 2. So what do you think, why this prepare ID is less than the prepare ID of or the accepted ID of the previous proposer? Why it happens? Do you have any idea?
So this is a new proposal. So uh, it could be that your ID is based off of when you joined the network, the ID number.
Yes. No, for every propose, the new ID will be generated. But
Oh,
proposer 2
okay.
is proposing with 50 here, right?
Oh,
Where proposer 1 is already prepared with the 100.
that could be the proposal two had sent this out a while ago, but due to technical malfunctions, it wasn't received until we got to ID 100.
That's correct. And one more, that's a good point. And one more thing is, when proposers, second proposer is broadcasting that prepare ID of 50, maybe the network on proposer 2 side is slow, or the during the proposer once proposer is circulating that message inside the network, proposer 2 may be sleeping. Okay, so proposer 2 is unaware that majority of the acceptors accepted with the new proposer. So upon this proposer message comes to all the acceptors, then the acceptors ignores this. Why? Because the new proposer ID is with the 100, right? So then the acceptors received this prepare message with this ID P, and they said they will check themselves that did they promise no to any of the previous IDP. If they already committed, then they will ignore it. If not committed, they will promise to ignore any request which is lower than your 100 here in this case, and then they will reply with the promise ID upon that. So then the proposer 2 understands that okay, the majority of the acceptors they gone through the proposer once prepare. So then try to propose the new proposal with the new ID if I have that. So then upon receiving this new prepare ID, then the acceptors receives this new proposer ID with 150, and they will check whether they want, because every acceptor is having two choices now. New proposer is there and the accepted ID is there. So in that case, the acceptors has it ever accepted anything that is assume the ID of your A. So then if yes, they reply with the promise ID accepted value, and if no, they reply with the new promise or new commitment ID. So upon this, the receivers, the acceptors will inform the proposer 2 that the promise ID 150, for this promise ID, the accepted ID along with the value will be given to proposer 2. We all are agreed on this particular propose, which is proposed by your proposer 1, and the value of that proposer is we are going for the dinner. So what the proposer will do now, the majority of the acceptors, they agreed with the proposer 1. So the proposer 2 have don't have any choice. So the proposer 2 he or she will also join the same value. Okay. So that is the proposer 2 gets the majority of promise message for this IP ID, the prepare ID. So it sends the accept request the ID that is accepted of 100, and the value is go for the dinner to the majority of your acceptors. So then it picks any of its choice. The proposer picks any of its choice whether will join or not. So that has it got any already accepted value from these promises. That means if S, pick the value with the highest ID. If no, pick the value of its choice, whether it wants to go with the 100 or go with the 150. So then based on that, the proposer 2 will also accept that request and inform all the acceptor that I will also join with this accepted request, and they will go with the same value. So how the majority works here, you can see if there are two proposers, proposer 1 and proposer 2, they prepare, proposer 1 prepare the IDP and broadcast among the network users. It goes to all the acceptors, majority of the acceptors. Okay, so then if the acceptor 1 is committed to that the propose, then give the reply with promise ID of the prepare ID, and acceptor 2 after that the proposer 2 is proposed with the ID 50 as we discussed in previous case, then that one is already accepted with the highest ID, so that will be ignored by the acceptor 1 and will be ignored by your acceptor 2 and accepting the previous proposer 1 proposal. And if the majority of these acceptors promised on IDP 100, then ID 50 cannot get through, so those acceptors will ignore it. So there are 3 acceptors are there, so out of that 2 are already accepted the propose of your proposer 1, then they will simply ignore it, and they will give the commitment to your proposer 1. So then if proposer 2 comes, it will be the agree with the new proposal that if proposer 1 is proposer 2 is proposing with the new ID, then the proposer new ID is accepted by your acceptors, and they will inform the proposer 1 that they are going with the new proposal which is proposed by your proposer 2. So that will be broadcasted in the network. Then the accepted request ID for your dinner will be the broadcasted among the acceptors, but the acceptors will ignore that they promise to go with the new ID, new commitment. So then that timestamp, during that timestamp, because the proposer 1 received this commitment and preparing a accepted request message and sending it back to your acceptor and waiting for that reply, for this accepted reply. During that time it will they ignore, so they don't give the reply to your proposer 1. So wait for a random period of time. When it is time out, then your proposer 1 may prepare the new proposal, and that will be broadcasted among the users. So there is no termination guarantee on this Paxos. Proposer 1 proposed, acceptors are accepted and replied during that proposer 2 proposed. So with the lower ID, so ignorance. Then after that proposer 2 is prepared with the new ID, which is higher than the previous proposer. Then for that the acceptors accepted it and replied to proposer 2. Then whatever the accepted request ID is there, that is ignored by your acceptors. When they ignore, they don't reply to your proposer. So proposer understand that okay, they might have committed to some other proposer, and they will try to the proposer will try to prepare a new ID, and that will be broadcasted. So it is a never-ending process in that Paxos that impact on the liveness in this Paxos. So the majority of acceptors, or the majority of acceptors that accepts a request with an ID and a value, then consensus has been reached, and the consensus is on the value. If not, the acceptors request with a lower ID, suppose, then that will not be accepted by the majority of your users or acceptors. So that would require a majority of promise with the lower ID, but we got for a higher one, so hence the acceptor request is ignored there, right? So The consensus is on the value, so we need the ID to maintain the current state of your the promise and accept, so that multiple value do not propagate in the network. So IDP is unique, that will maintain the status that whether it is a previous proposer or the new proposer. So this accept request with the higher ID, but a different value will not be accepted by the majority, because at least one acceptor will the piggyback the previously accepted value. That is, remember, two majority implies that there is a common node here in our example. So this Paxos, how it is useful for the leader election process, that prepare a ID and that will be broadcasted among the acceptors, and uh, based on that prepare ID, the acceptors replied, they promised that. So the majority of the acceptors, they promised to that particular prepare ID. So the proposer one accept request, the replies with accept request ID, that will be broadcasted among the acceptors. So then acceptors will select a leader with that accepted ID. Their accept ID is 100, and that reply will select the value as your leader in this case. So in this multi-Paxos, the applications often need a continuous stream of agreed values, because the application of this multi-Paxos is one is your flights. So when more than one flights they are trying to land at a time, in that case, it must be updated every time, so that which leader is getting chance to the land in the airport. So the applications often need a continuous stream of agreed value. So they commit the transaction in a replicated database. So each transaction needs a consensus to be agreed upon by the replica, by majority of the people in this case, this network. So run this multiple instances of your Paxos with the different round numbers. So that is achieved by your timestamp and doing the hash function there. So each value is associated with a round number in this case. So if a value is already accepted for a round nth round suppose, then ignore that accept request for a different value under round n. So first they agreed, suppose at the nth round agreed to go for dinner, and in the accept request, which again they broadcasted by your promiser, instead of go for, say that go for movie, this will be ignored. And the forward and accept ID and round number with value only when no value has been agreed upon the round n. So this is the case of your multi-Paxos. So with this, I would like to stop this session here, as because of